be here. We'll be going through introduction as well as getting into machine learning in deep dive. Today we're not going to be going through natural language processing. That's something we will plan on getting into probably later in the year. So much time. You can hear me.
The problem is sharing the slides. So we're going to show you slides.
So we'll be going through two modules: introduction to data science and machine learning, as well as machine learning deep dive. Is one thing I'd like to mention before we go on. This course content is being actively developed by Delta Analytics, which is a Bay Area nonprofit that aims to empower communities to leverage that data for good. So these slides were made by Delta Analytics. I'm just going to go through them and help you understand what data science and machine learning is. Yeah, so let's begin. So this module we'll be talking about, we'll be getting into data science and machine learning, what it what the whole process is about. So yeah, we're going to be talking about what data science and machine learning is, how do you define a research questions, what are observations, what are features, what are outcome variables, and then an introduction to Kiva data. Okay, I'll start with introducing Kiva data, which is what we're going to be looking at mostly. Kiva data is an international micro lending. Kiva is an international micro lending nonprofit company that links lenders to borrowers for amounts as little as $25. Kiva data is publicly available through the API. I've downloaded data from Kiva that's in Kabo. And I split it into two regions, that's Kenya and Uganda. You can find that in our GitHub repo, that's Africa's Talking GitHub repo, which I'm going to share after this video. So yeah, let's try to understand what data science is. Data science is an umbrella term that encompasses data analytics, data mining, machine learning, and other related disciplines. Yeah, as well as artificial intelligence. Machine learning is programming by example. That is the practice of using algorithms to use data, learn from it, and then forecast future trends for the topic. So machine learning basically involves a type of learning where you feed data into a certain model and then it's able to predict certain outcomes. Yeah, so I've defined data science as well as machine learning. So humans learn from experience. Everyone learns from experience. Machines as well are able to learn from experience by following instructions through the data that we give it. Yeah. So humans learn from experience. Traditional software programming involves giving machines instructions, which they perform. Machine learning also involves allowing machines to learn from raw data, so that the computer programs can change when exposed to new data. That is learning from experience. Machine learning is an interdisciplinary field, so it encompasses computer science, statistics, and mathematics, and it uses data to answer questions. Yeah. So you get data and domain knowledge, you get insights from the data, and then we perform a certain action. So here we have an example of machine learning. So we have Dr. Delta who works to diagnose patients with malaria. However, it takes a long time for her to see everyone. So Dr. Delta decided to take historical patients' data and build a machine learning algorithm that predicts whether a new patient will have malaria or not. Yeah, so the algorithm, the machine, learns from past data like a human would, and is thus able to make predictions about the future. So there are various applications of machine learning. One of them is determining your credit rating based upon cell phone users or credit scoring, etc. There's also determining the topic of a piece of text, facial recognition, as well as recommending movies you like. This is clearly recognized in Netflix. So yeah, data science and machine learning helps us answer questions, but how do we define the question? How do we define the question that will help us make our prediction? So that's what we're going to look at next. So before we even get to the modeling phase, we have to learn about our data and define our research questions. So that's usually the first stage. What is the problem that you're trying to solve? After that, we'll do data validation and cleaning, exploratory analysis, and then modeling, and then checking the performance of our model. 80% of our time is really spent in cleaning data and exploring it. Machine learning takes place during the modeling phase. Yeah, I've mentioned that. So what's a research question? So a research question is a question you want our model to answer. It's the problem that you want to solve. Examples of such questions are: does this patient have malaria? Can we monitor illegal deforestation by detecting chainsaw noises in order streams from rainforests? Another example is this person credible to get a loan or not? Is this email spam or not? What is the price of this house? etc. That are examples of research questions. We may have a question in mind before we look at the data, but we will often use our exploration of the data to develop and refine our research questions. So most of the time, we'll go to our data and then see if the data will help us answer our research question. If not, we go back, refine the research question, and then get back to exploring. If we don't have a lot of data, we go back, get data that will help us answer our research question. So yeah, before exploration, we usually do data validation and cleaning. Data preparation accounts for about 80% of the work of data scientists. So most of the time, you find data scientists going through data, cleaning it, putting it in the right order. Yeah, and that's where the most work is, because if you have shitty data, you will have a shitty model. Yes. Why do we need to validate and clean our data? Data often comes from multiple sources, so you have to check if data aligns across different sources. Data is also created by humans, and humans are not free. Okay. It's free from human bias and errors, and does the data need to be transformed? We'll get into that a bit later. So yeah, data cleaning involves identifying any issues with our data and confirming our qualitative understanding of the data. So we need to check, does our data have missing data? If it does, is it systematic or is it random? We also need to check time series validation. Is the data for the correct time range? Also the data type or our variables of the right type. We check date time. Is it a numeric variable? Is it a categorical variable, etc. Data range, are all values in the expected range? Are all loan amounts greater than 0? So these are just some examples of data exploration, data cleaning. So the following are steps that are used through data cleaning. We check missing data, time series, that is if your data has date time. We also check date types and then transforming variables. So there are three types of missing data. There's missing completely at random, there's missing at random, and missing. So missing completely at random is whereby no pattern is in the missing data. This is the best type of missing you can hope for. There's also missing at random. There is some pattern in your missing data, but not in your variables of interest. And there is missing not at random. there is a pattern in the missing data that systematically affects your primary variables. That's the worst missing data you find. So very few data sets have no missing data. Most of the time, you have to deal with missing data. The first question you have to ask is what type of missing data you have. So, sorry. So here's a quick example. Let's try to understand a little bit more about the types of missing data that we have. You have survey data from a random sample of high school students in the US. Some students did not participate. So some students were sick the day of the survey. And we have another type of missing data. Some students declined to participate since the survey asks about grades. So in the first so this is bad, this is okay. Sometimes we can replace missing data. So some of the solutions are we either drop missing observations and just take observations that have all values. We populate missing values with average of the available data and impute data. So here are some common imputation techniques whenever you come across missing values. So take the average of observations. You do have to populate missing observation. That is, assume that this observation is also represented by the population average. Use an educated guess. Sometimes you can just guess and fix it in. It sounds arbitrary and often isn't preferred, but you can infer a missing value. Use common point imputation for a rating scale using the middle point from most commonly chosen value. For example, on a 5-point scale, substitute a 3 the midpoint or a 4 the most common value in many cases. This is a bit more structured than guessing, but it's still among the more risky options. Use caution unless you have a good reason and data support using the substitute value. Yeah, but most of the time people usually either drop, which is also not usually advised, or use the average of non-missing values. There are also other ways you can compute missing data. So if we have observations over time, we need to do time series validation. So ask yourself if the data for the correct time range, are there unusual spikes in the data over time? What should we do if there are unusual spikes in the data over time? So there can be systematic spikes and random spikes. So for certain data sets, the sales data, for example, systematic seasonal spikes are expected. So around Christmas, we would expect a spike in sales revenue. This is normal and should not necessarily be more. Okay. So sorry about that. So how do we address unexpected spikes in our data? Yeah, so there's a systematic spike. So we'd expect a spike around Christmas and there's a random spike. If the spike is isolated, it's probably unexpected. We may want to remove the corrupted data. For example, if for 1 month sales are recorded in Kenyan shillings rather than US dollars, it will inflate sales figures. We should do some data cleaning by converting to dollars or perhaps remove this month. Yeah. So here we check data types of variables. So many functions in Python are type specific, which means we need to make sure all of our fields are being treated as the correct type. So here we have data from Kiva. We have loan amount, partner ID, sector, and posted date. Loan amount is an integer. Number float shows a number of decimal places. Sector is a string or a text field or categorical variable, and posted date is a datetime value. We also have boolean, which can be true or false, also called indicator or dummy variable. Yeah, so let's try to see if you've understood data cleaning. So, for example, there is an observation from the Kiva loan dataset that says a loan was fully funded in the year 1804, but Kiva wasn't even funded then. So, what do we do? So, in this case, we will either this case we'll probably drop it or just go back to the data documentation and see if that's an error. If it's an error, we can change it. Yes, that's the answer. Consult the data documentation. If no explanation exists, remove this observation. Okay, we have another question. There is an observation that states a person's birthday is on 12th, that's December 1st, 1880, but the age variable is missing. What do you do? So this is easy. We just compute the age variable. Yeah, we can calculate age. It's actually 1980. So 2017 minus 1980, we get 37. So this is one of the ways we can deal with missing data. This question illustrates how we may be able to. No video, no video. How is that? Okay. Sorry about that. Let me go back to data cleaning quiz. So, yeah, we have some few questions. While data cleaning, there is an observation from the Kiva loan dataset that says a loan was fully funded in the year 1804, but the Kiva wasn't funded in that. Like, what do you do? So, if you come across such a situation, either go back to the data documentation and see if that's an error that was made, the data was being filled, and if it's not, we just delete it. Yeah, we just delete it. Yeah, consult data documentation. If no explanation exists, remove this observation. So question 2 is an observation that states a person's birthday is on December 1st, 1980, but the age variable is missing. What do we do? In such a case, we can just compute age. We can calculate age by subtracting current year minus the birth date. Yeah, that's pretty simple. The variable amount funded, for example, in the Kiva data, has values of both NAs and zero. What do I do? So for most of the time, we go back to the data documentation and see if that's an error or if there's a significant difference between an A and 0. So, sorry. Yeah, so check documentation if there is a material difference between an A and 0. If I'm not sure what currency the variable amount funded is reported in, what do I do? In such a case, we check the documentation and other variables and convert amount funded into the appropriate currency. So, final note, the examples that were presented were very specific. You may or may not encounter these exact examples. This data cleaning is very often idiosyncratic and cannot be adequately completed by following a predetermined set of steps. So you might encounter a very totally different kind of data, and you'll have to do some different kind of data cleaning techniques that we've not even talked about. So yeah, data cleaning is very extensive, and it actually depends on the type of data that you have, where you've collected your data, and a lot more. So after cleaning data and validating, we usually do exploratory analysis. So the goal of exploratory analysis is to better understand your data. So exploratory analysis can reveal data limitation, what features are important, and inform what methods you use in answering your research questions. This is an indispensable first step in any data analysis. So we have to do exploratory data analysis, just have an idea of how our data looks like, and the distribution of our data. So the various steps that we take or various visualizations that we make to explore our data. So we have histogram, which basically checks the distribution of our data. There's scatter plots that checks the relationship between two variables. Correlation that checks correlation. Scatter plots are really almost used the same way. Box plots are used in visualizing summary statistics such as mean and median and frequency mode, etc. Yeah, so once we've done some initial validation, we explore the data to see what models are suitable and what patterns we can identify. So yeah, like I said, histograms tell us about the distribution of the features. So we have various distribution. The one that's commonly used is the normal distribution, which is also known as the bell curve distribution. So here we have height of data of a group of people. We see that most of the people in the group are between 149 and 159 centimeters tall. This is an example of a scatter plot. So a scatter plot is used to check the relationship between two variables. So here we have amount funded and sorry, amount funded and amount requested. Scatter plots visualize relationship between any two features as points of the graph. So as we can see, there's a positive relationship between amount funded and amount requested. So what can we conclude? So here we can already see a positive relationship between amount funded and amount requested for Kiva loan. So it looks like there is a strong relationship between what loan amount is requested and what loan amount is funded. So do we assume that the more amount you request, the more amount that you're going to be funded? Okay, we'll talk about this a bit later. So correlation is a useful measure of the strength of a relationship between two variables, and it usually ranges between -1 and 1. So we usually have positive correlation, high positive correlation. This is where the y-axis increases as the x-axis increases. Here we don't have, there's some correlation, but it's not high, no correlation at all. This is negative correlation. In this case, as the x-axis increases, the y-axis decreases. there's some correlation, but it's not so high, and this is perfect correlation. So let's go back to okay, let's talk about this correlation does not equal causation. So let's say you have an executive at a company, you've gathered following data spent on advertising and sales. Yeah. So based on this graph, it says this is the amount that's spent on advertising and this is the amount that's spent on sales. The x-axis spent on advertising, the y-axis spent on sales. So based on the graph and positive correlation, you'd be tempted to say the amount spent on advertising caused an increase in sales. But it's also possible that increase in sales will lead to increase in the amount spent on advertising. So just because there's a correlation between x's and y, it doesn't mean that x causes y or vice versa. So yeah, let's go back to the graph we had earlier, the scatter plot graph, where we had amount funded increasing as amount requested increases. So if you wanted to request a loan to Cuba and were presented with this graph only, what should you conclude? Like I said before, you'd assume that the more amount I request, the more amount I get funded, but that doesn't really make sense. So common sense tells us that this conclusion doesn't make a lot of sense. You can't say that amount requested, the more amount you request, the more amount you're going to be funded. That's not usually the case. Yeah, so that's an example of why correlation does not equal causation. So let's go through some summary statistics. These are very simple statistics that are used in data exploration. The mean, median, and the frequency. They let you know what is in your data and how your data looks like, and if you have any outliers in your data. So mode checks what occurs most often, median checks the middle value, and the mean shows the average. So here we have an example of a box plot. So box plots are useful visualization, depiction of certain summary statistics. So this is how box plots usually look like. The tip at the bottom shows the minimum value, where the tip ends, that's like the beginning of the box plot, shows the first quartile. The line in the middle shows mostly the mean or median. At the top, where the line is starting, that's the third quartile, and then the end of that line is the maximum. These dots on top here are called outliers. So outliers just shows values in your data that are not within the data that you have, so that they are known as extremes. So you might see that your data has a mean of 36 and there's a value somewhere that's like 100. So that's an example of an outlier. So yeah, for main research questions, so we may have a question in mind before we look at the data, but our exploration of the data often develops or refines our research question, like I had said. So how do we define our research question? So we start with a research question. We ask if we have enough data that can be used to answer our question. If we don't, we go and find more data. If we do, we check if the data is labeled. If the data is labeled, check the data types, what are the data types of our variables, and then we go next and see if our problem is supervised or unsupervised. We'll get to that a little bit later. So checking if we have enough data requires data processing and validation. That's where we do a lot of data cleaning, in data processing and exploration. Next, we check if it contains an outcome feature Y. So if it does, there's a correction here. Supervised learning. If the data is labeled, we use supervised learning. If the data is not labeled, we use unsupervised learning. You'll never find a situation where we'll cover both supervised and unsupervised at the same time. If your data is labeled, that's a supervised problem. If it's not, that's unsupervised problem. So let me give you an example. So for example, we are predicting whether an email is spam or not. We have one variable, let's say, showing all the emails that you have received, and then they've been labeled as either spam or not spam, and we're going to predict that. So that's our Y, that's our outcome feature, also known as the target variable, and that's why we're going to be using supervised learning methods. But in unsupervised learning methods, there is no Y variable. We're just looking at how the data is and trying to see if we can find anything meaningful from that data. Cool. So here's an example of this is how the Kiva data looks like. So given the data, Kiva data below, we may find a few questions interesting. So loan amount requested by Kiva borrower in Kenya. And we also have location town. So one possible research questions might be, does the loan amount requested vary by town? That's one question. Can you think of any other questions that we might ask? So we might ask, does lender count vary by town as well? Yeah, that's also another question we might ask. So how does loan amount vary by town? So there is a reasonable research question because we will expect the amount to vary because the cost of materials and services varies from region to region. For example, we would expect the cost of living in a rural area to be cheaper than in an urban city, but that will be some interesting things to find out. So next is modeling. So we talked about data cleaning, how you go about missing data, exploratory analysis, defining a research question, and then we are here modeling phase. So all models have three key components. That is a task, a performance measure, and a learning methodology. So a task, what is the problem we want our model to solve? Yeah, so that's where we define our research question. Learning methodology, machine learning algorithms can be supervised, like I talked about, supervised or unsupervised. This determines the learning methodology. So if your data is labeled, that is supervised. If it's unlabeled, that's unsupervised. Performance measure, quantitative measure we use to evaluate the model's performance. Yeah, so here we check how our model is performing. So we'll go over the machine learning task and learning methodology in the next module, where we'll get deep into machine learning and that whole modeling process. So yeah, this is the end of our first introduction to data science and machine learning. We've talked about what machine learning in data science is, how we define a research question, what observations are, what are features, what are outcome variables, introduction to keyword data as well. So these slides are available on Africa's Talking GitHub account. I'll share the link with you guys at the description area. Next, we're going to be looking at machine learning, and yeah, in about 5 minutes. Thank you.